To see the Yellowstone landscape through the eyes of a geologist is like reading a thriller novel with all the twists and turns. Yellowstone is a real page-turner. Ken Pierce was a geomorphologist. He was trained to look beyond the landscape and visualize the processes that created it. Like seeing a time-lapse movie of geologic evolution flicker in the mind's eye. As a young PhD working for the preeminent United States Geological Survey, Ken's first assignment in 1965 was to map the glacial history of Yellowstone. It must have felt like a daunting task as he set out on horseback with fresh eyes to decipher over 150,000 years of glacial sculpting on the Yellowstone Plateau. There is a wonderfully descriptive term, palimpsest, derived from ancient Greek, that geomorphologists use to evaluate any landscape. In the ancient world, skins or parchment were used as a surface for early writing. In order to reuse the parchment, scribes would wash or erase the original script and write over it. Inevitably, faint shadows of the earlier text could be seen in the background. In geological terms, palimpsests represent layers of different age deposits or landforms. On the Moon, for example, meteor craters occur on top of and cross-cut older features. This is easy to see when there is no vegetation to obscure the terrain. Viewing the landscape as a palimpsest allows you to begin to see the sequence of events that tell a geologic story. Ken's challenge was to decipher the complex palimpsest of the Yellowstone Plateau. When Ken started his fieldwork, it was generally thought that glaciation of the Yellowstone Plateau didn't crest the summit of Mount Washburn, and that glacial ice moved from north to south. Glacial erratic boulders of Precambrian metamorphic rock, like this one near Canyon Village, were good evidence of this north to south flow, because these boulders originated in the Beartooth Uplift to the northeast. But when Ken surveyed the summit of Mount Washburn, he discovered a much more complex story.
We're here on the summit of Mount Washburn, which is in the central part of Yellowstone, just north of the center. There's glacial striations right on the crest of this range, indicating flow from the south to the north. Glacial striations are where small rock fragments at the base of the ice scrape across bedrock and leave a scratch, just like kind of like a nail would leave a scratch on wood. And the polish is the same idea. It's like sanding the surface with the base of a glacier. This was quite a discovery because it was debated whether ice got as high as Dunraven Pass. And the main idea was that the ice came from the north and went to the south.
His supervisor at the USGS was also mapping in the area. He agreed with the original idea that Yellowstone glaciers moved from north to south. Indeed, there was early north to south flow that brought erratics from the Beartooth Uplift. But Ken found contradicting evidence of significant south to north flow on the crest of Mount Washburn. As the debate continued, Ken decided to take a different approach.
And we went out in the field and looked at these things and argued, and there wasn't any resolution. And then I decided, well, I'm just going to have to look at a different way to approach this problem. So I made what's called a glaciological analysis. What I was doing is called glacial geology, and glaciology is to use physics as applied to glaciers. And I tried using physics as applied to past glaciers, ones that aren't here, but looking at the reconstructions. And this motivation was very fortunate for me. It made me look much deeper into this another branch of this science and try to see if I could work this out. We're at around a little above 10,000 feet, but it now appears that in the last glaciation, ice built up to about 2,000, 3,000 feet higher than us and overrode the crest of this range, headed northward towards where it formed an outlet glacier at Gardner, and then flowed down the Yellowstone Valley for another 40 miles to its terminus. In the area of the Grand Canyon of the Yellowstone, this sequence is complicated in that it starts out with glaciers coming from the north, advancing up the canyon of the Yellowstone River to Canyon Village, depositing the big glacial erratic that sits there. And then in full glacial times, ice was going 2,000, 3,000 feet higher over the top of Mount Washburn, and a big ice cap was on the plateau. Then the ice cap melted down on the plateau, and ice advanced from north to south back up the canyon.
A story in excruciating detail. That's how Ken described his professional paper on the history and dynamics of Yellowstone glaciation. For his innovative approach, using physics to solve a geological problem, Ken received the prestigious Kirk Bryan Award from the Geological Society of America.
I think this is what motivates a lot of science, is you sort of end up having to look at something new to try to see if you can solve an argument.
In later years, Ken worked with Joe Liccardi of the University of New Hampshire to refine the extent and timing of Yellowstone glaciations. At full glacial, the Greater Yellowstone Glacial System was the largest in the Rocky Mountains and covered some 20,000 square kilometers. So why did the Yellowstone Plateau attract such massive ice buildup? Though it might appear to be counterintuitive, Pierce and Liccardi determined that the Yellowstone hotspot facilitated glaciation on the plateau. Over the last 17 million years, the North American plate has moved over the stationary Yellowstone hotspot, creating a lowland arc of volcanism across today's southern Idaho, known as the Snake River Plain. At the head of the Snake River Plain is the current Yellowstone Volcanic Center. The three great Yellowstone eruptions, Huckleberry Ridge at 2.1 million years, Mesa Falls at 1.3 million, and Lava Creek at 600,000 years ago, deposited massive, welded tuff, rhyolite, and basaltic lava flows, adding to the elevation of the plateau. In addition, expansion of the magma chamber beneath the current Yellowstone Volcanic Center continues to increase elevation of the plateau to this day. A combination of these factors contributed to what Pierce called the Yellowstone Crescent of High Terrain, at the apex of the Snake River Plain, similar to a mountainous cul-de-sac. Ice buildup to form mountain glaciers depends on climate, elevation, and weather. During the last glacial maximum, the average temperature was as much as 14 degrees centigrade, or 25 degrees Fahrenheit, lower than today. The crescent of high terrain provided the elevation. To complete the trifecta, the low elevation and orientation of the Snake River Plain allows Pacific, moisture-laden weather to funnel right to the Yellowstone Plateau, where it precipitates moisture on the high terrain. For these reasons, the Yellowstone ice cap grew to over 1,000 meters higher than Mount Washburn and changed the direction of ice flow to the north. In keeping with the palimpsest metaphor, a geomorphologist sees a glacial terrain as a series of overlapping terminal and lateral moraines, or glacial advances, of different ages. A moraine consists of the poorly sorted boulders, sand, silt, and clay that is dropped from the ice as it melts and recedes. You can determine the farthest advance of a glacier by its terminal moraine. Lateral moraines are deposited along the sides of a glacier as it advances and retreats.
We're overlooking the black-tailed deer plateau, a large meadow terrain in northern Yellowstone, laid down during glacial recession. The bulk of the deposits are inside what we call the Deckard Flats limit, and in this large plateau, a lobe of the ice from the Yellowstone River area spilled over into this area and pushed out into this large kind of a plateau. As this ice receded from the outer to the inner position, at each position, a set of moraines, and in the central part of the plateau, ice marginal cane gravels was deposited. So we have this sequence of recessional deposits that probably has 15 different stages that you could subdivide out of it, each of which represents an ice margin and the deposits laid down along this ice margin.
To understand the timing of glaciation, Pierce mapped glacial moraines throughout the northern Yellowstone region. He dated the moraines using obsidian hydration and potassium-argon dating methods. Obsidian is formed by rapid cooling of silicon-rich viscous lava at the Earth's surface. The result is amorphous volcanic glass with no crystalline structure. Obsidian hydration dating was a breakthrough in the 1960s. At that time, Irving Friedman of the USGS developed a method which measures the rate at which water molecules infiltrate a freshly broken piece of obsidian. This could be translated to the time when the surface was fractured or when the moraine was deposited. Obsidian hydration is commonly used to date Paleo-Indian projectile points. With this method, archaeologists can tell approximately when a point was manufactured.
Yellowstone is rich in obsidian, and so this was a wonderful place to go and see if we could date glaciations based on this technique called obsidian hydration dating. And in Yellowstone, we had the added advantage that we had these obsidian flows that had potassium-argon ages, so we could measure the hydration on those and use those for calibration, and then measure the hydration on glacial deposits where the glacier had scruffed these stones against each other and made fresh surfaces, just like making a projectile point, except not near as fancy, and measure the hydration thicknesses, and with this calibration based on the potassium-argon dated flows, date the timing of glaciation.
Through his detailed mapping, Ken had worked out the relative sequence of Pinedale glacial advances and had made estimates of the ages of the moraines. But geochronology had advanced greatly by the time Pierce and Liccardi worked together, and a new, out-of-this-world technique allowed them to refine Ken's earlier timelines and assign numerical ages to the Pinedale glacial stages. By the end of the 20th century, human imagination had harnessed cosmic rays to help date moraines that were left by a receding glacier. Cosmic rays have a short wavelength and can't penetrate a thick ice mass until the moraine is nearly exposed. The cosmic rays bombard the atoms in the rocks and create elemental nuclides or isotopes. It can be counted with a mass spectrometer. The counts for certain elements suggest how long it has been since the moraine was exposed or deglaciated. Ken had recognized two major glacial advances in Yellowstone, as evidenced by their morainal deposits. The older advance is called Bull Lake and was deposited some 150,000 years ago at the end of the Illinoisan glacial period. It was then when the Precambrian erratics from the Beartooth Uplift were deposited. The more recent glacial advances, known as Pinedale, came near the last glacial maximum around 21,000 years ago. This is when the ice cap topped Mount Washburn by nearly a kilometer, flowing north, and joined several other glacier source areas coalescing into the Paradise Valley to create the Yellowstone Outlet Glacier.
During the last glaciation, the Yellowstone area, when the ice built up to its full amount, which we call full glacial, 95% of the park was covered with ice, and ice was going over the top of Mount Washburn, which is the highest place in the middle of the park. It's 10,200 feet high. And so essentially there was a thick ice cap on Yellowstone. It was both on the Yellowstone Plateau and it was on these rimming mountains that surround the edge of the plateau. And how that built up to that stage and how it receded from that stage turned out to be quite a complex sequence. The ice on the Yellowstone Plateau didn't get started until the other glaciers were well underway, and then it built up and became nearly the dominant part of the whole system. And then during deglaciation, it melted first, and then the glaciers on the plateau from the surrounding mountains advanced out onto back onto the plateau.
During the Pinedale advances, ice-dammed lakes would form in places like Lamar Valley, Hayden Valley, and Yellowstone Canyon. When the ice dams broke, torrents of water with massive boulders, mud, and debris would rush into the Yellowstone River drainage and wash out into Paradise Valley, near Gardner, Montana.
These deposits had been seen and were thought to be glacial moraines, although they did seem unusual. And at the same time, there was a grand debate going on the origin of the channeled scablands. And channeled scablands are out in central Washington along the Columbia River. And they're part of the continental ice sheets coming out of Canada dammed a large lake along the Clark Fork, particularly in the Missoula area, and that lake was up to 2,000 feet deep. And when that lake catastrophically drained by failure of the ice dam, great floods went out into central Washington and crossed what's now called the channeled scablands. This area was eroded by these floodwaters. And in places below narrows and below canyons where these waters were spreading out again, we have similar features to this, bouldery deposits with a kind of ripple-like form. And as flood deposits were getting better understood by studies there, it became very obvious that this was something similar. The boulder concentration on these ridges is considerably higher than you find on moraines. And that's because it's water-laid deposit. There's no fine matrix between the boulders. This is boulder on boulder kind of deposit. And then their general form, their spacing. Probably the most impressive thing is the way they look from the air. And that's true also of the channeled scabland. You can see the forms of the ripples, and they just look like stream forms, except they're so much bigger than what you normally see that if you get the air perspective, you can see the sort of fluid flow aspects of what was creating these giant ripples. Right ahead of us is a mid-channel flood bar that has what we could call giant ripples on it. These are spaced 40 to 60 feet apart and have 3-foot boulders on them. And this was formed by floodwaters maybe 200 feet deep that came down the Yellowstone through this area. May have been a morainal topography originally, and then the flood came across it and swished out all the fine material and left the boulders armoring the surface. This feature's out in the middle of the valley. The waters were on either side of it as well as over it, and swirling around and leaving these ripple-like forms with boulders up to 3 feet across. And the boulders often show a lot of signs of bashing together, where different boulders crashed into each other as they were swirled around in this torrent released by probably a ice-dammed glacial lake, either up in the upper Lamar Valley or Grand Canyon of the Yellowstone, or both. There is good evidence that there were multiple floods, and that's characteristic of ice-dammed lakes, that the water gets deep enough to float the ice or release the ice, then the dam releases and gives way, and then the lake catastrophically drains from behind the ice dam, and then the waters rush on down valley. And here down here the estimates of the floodwater depth is about 200 feet. At the mouth of the canyon where the water was coming out, have an estimate of near 300 feet. Here we can see the patterning here. Here's a ripple crest. Over there is another one. Over here, a third one, and then beyond that, fourth one, fifth one, sixth one over there where the probably it's a raven perched. And the boulders, they get pretty big. There's a good sized one right over here. This one's interesting in that, let's see, maybe get on this side here. There's a nice big boulder, and these are bash marks here where corners have been knocked off as this thing was banging against other boulders in this slurry of everything from boulders to gravels to sands to silts to clays was swirling down valley, being carried by these enormous currents. Must have been a tremendous thing to witness if anybody was around to see it. And you sure would want to be well off the valley floor, because everything in its path would have been tremendously affected by these floodwaters.
From the time Ken first recognized the bouldery deposits as so-called giant ripples caused by catastrophic flooding, the timing of the floods was a burning question in his mind. Finally, with cosmogenic dating, Pearson-Liccardi dated the most recent flood deposits to approximately 14,500 years ago, pushing the time of Yellowstone deglaciation much later than previously estimated.
One thing I'd like to talk about is how this glaciation that covered all of Yellowstone and really much of the whole greater Yellowstone area or greater Yellowstone ecosystem, how that affected the landscape. And this glaciation formed many what you might call human scale features, something that you can climb in a few minutes, something's about as tall as you are. There's all sorts of things on this scale that are this fine shaping of the landscape, either by sculpting or by deposition, that the glaciation accomplished. The first thing it did is it scraped away all the existing soils, The glaciers erode material in near their source areas, and then they deposit a train of material as they go down valley. And then as the glacier retreats, it's depositing material. So that much of the landscape is covered with materials that are either deposited by glaciers or terrain that was eroded by glaciers. And this greatly influences the soils in the area. The material that's in the soil is the material that the glacier got a hold of. And if it's rhyolite, it's not going to be very good, have good nutritious values for the trees. The nutrients are quite poor, and it'll result probably in a lodgepole pine forest. Other materials produce the spruce fir forest. The fine sediment holds water high in the soil and produces the meadowlands. The gravels are very well drained, and the water disappears, and so it's only plants that can survive with low water budgets. In the lower elevation areas, this is the sagebrush, the big sagebrush flats of Jackson Hole, the big sagebrush flats of the Yellowstone Valley north of the park. So much of the landscape and the soils are related closely to what the glaciers did. We're going to be working next week looking in the Black Canyon for the evidence of the flood deposits. They've been mapped by me 20 years ago as encompassing Crevice Lake, which is over 100 feet above the present river. We'll be looking into that and seeing if that really makes sense, and looking at Crevice Lake as a coring site because it has laminated varve sediments in it.
In the next episode, Ken, along with paleoclimatologist Cathy Whitlock and former Yellowstone chief naturalist John Good, explore the mysteries of Crevice Lake.